This video will go over section 4.8 on polarity of molecules. So this is very different from the polarity of just the bonds. This is about the polarity of the molecule as a whole. And so the classification of a molecule as polar or non-polar depends on, first, the polarity of the individual bonds. If you have no bonds that is polar, then the molecule cannot be polar. And then if you have polar bonds, it depends on the overall shape of the molecule. So non-polar molecules generally have no polar bonds, right? So these two molecules on the left are examples of non-polar molecule. The CCl molecule has twice the same atom, so they will pull with the same strength on electrons, and so it's a non-polar bond. And so if you have no polar bonds in a molecule, the molecule cannot be polar. The CH4 molecule here has only CH bonds, and we saw that the CH bond has an electronegativity difference of 0.4, which is not enough to make it a polar bond. So the CH bond is non-polar, and so the molecule is also a non-polar molecule. And non-polar molecules generally have individual dipoles that cancel due to symmetry. So sometimes you have molecules that have polar bonds, but they cancel due to the symmetry of the molecule. And then the overall molecule is non-polar. An example here as with CO2, carbon dioxide. It's made of 1 carbon and 2 oxygen. The molecule has a linear shape. The carbon here in the center is less electronegative than the 2 oxygens, but the 2 oxygens pull with the same strength. And because they pull with the same strength in exactly opposite directions, then those two dipoles, they have the same value, but they are opposite one another, so they will cancel. So the dipoles here cancel, and CO2, the molecule as a whole, is non-polar, even though it has polar bonds. Another example with BF3. BF3 has a trigonal planar shape. It's a flat structure with the F being equally distant from each other and forming a triangular isocell triangle around the boron. And so each fluorine pulls with the same strength, pulls the electrons towards themselves. B is less electronegative than fluorine. And so we have 3 dipoles pulling away from the boron, but they all pull with the same strength, and they pull at equidistant directions. So it's a symmetrical molecule, and because of that, it cancels the 3 dipoles. So all dipoles cancel, and there is no net dipole. And so the molecule of BF3 overall is non-polar, even though it has polar bonds. So polar molecules generally have 1 or more polar bonds. So you need to have necessarily at least a polar bond. So the example here on the left shows formaldehyde, which has 1 polar bond, the CO bond. The CH bonds are non-polar. And there is nothing to cancel that dipole. So then the molecule is also polar. And it has the same net dipole than the dipole of the bond. Polar molecules also have individual bond dipoles that do not cancel. You can have more than 1. For example, the molecule of ammonia, NH3, has 3 polar bonds. The NH bond is polar. The electrons are pulled by nitrogen. So the way it is drawn here, the electrons are pulled upward towards the nitrogen, and the hydrogens are depleted of electrons. And those three dipoles pull at equal distance from each other, but they all pull upward. It's not a flat structure, so they will not cancel. And the overall dipole for the molecule is going upward, you know, starting between the three hydrogens, going up towards the nitrogen. And so ammonia is a polar molecule. The three dipoles do not cancel, and they reinforce into a net dipole. Another example with CH2Cl2. So the C-Cl bonds are polar, but the CH bonds are not polar. So we have two CH bonds that are not polar, and then on the other side we have two C-Cl bonds that are polar, and their two dipoles are going towards an overall same direction. And so they do not cancel. They add up into a net dipole that is in between the two chlorine. So coming from the carbon, going in between the two chlorines. So that's the direction of the net dipole for this polar molecule. So let's practice determining the polarity of a molecule. So when you're given a formula, first you want to determine if you have polar bonds, because if you have no polar bonds, then you can stop there. So let's go through an example. The molecule of OF2, let's determine if it's polar or not. So in OF2, there is only one kind of bond that can be polar. It would be the OF bond. So you look at the electronegativity of oxygen, and it's 3.5, and the electronegativity of fluorine is 4.0. So you do calculate the electronegativity difference between 4.0 and 3.5, and that's a value of 0.5. According to the table on electronegativity difference and bond classification, a value of 0.5 is considered a polar covalent bond. So the OF bond is a polar covalent bond. So because we have polar bonds, we will need to determine the Lewis structure and the shape of the molecule and see if the polar bonds cancel or not. So once you have worked out the Lewis structure, it should look like this. Oxygen is in the center. It's surrounded by the two fluorines. There is a single bond between each fluorine and oxygen. And oxygen has two lone pairs. So now let's determine the shape of this molecule. So oxygen is the central atom. So you count the number of electron groups around oxygen. And oxygen has 4 electron groups, which are 2 bonded atoms and 2 lone pairs. And if you look at the table in your reference packet and you follow the line where it starts with 4 electron groups, 2 bonded atoms, 2 lone pairs, the molecular geometry is bent from tetrahedral. So it's bent, and then we have 2 dipoles that go in the case of if the molecule is drawn as on the slide here, they go downward. So they pull, each fluorine pulls on the electrons. They are more electronegative than the oxygen. And the 2 dipoles are going in an overall same direction. So you end up with a net dipole that goes from the oxygen towards the 2 fluorine. And so the molecule OF2 is polar because the dipoles don't cancel. They add up into a net dipole. Let's practice some more with the molecules CCl4 and CH2Cl2 and determine if they are polar or not. So you want to pause the video and work this on your own. before you watch the answer. So let's start with CCl4. So in CCl4, you have the bond CCl. Let's look at the electronegativity difference between carbon and chlorine. Chlorine has an electronegativity of 3.0. Carbon has an electronegativity of 2.5. That's a difference of 0.5. So according to the table that classify bonds depending on the electronegativity difference, a difference of 0.5 is considered a polar bond. So the CCl bond is polar. So next we need to determine the shape of the molecule, and if you have worked out the Lewis structure, the 3D drawing of the CCl4 molecule is a tetrahedral shape. So here we have the tetrahedron with the carbon in the center and the 4 chlorines around. And the dipoles here, the little arrows, are showing that each CCl bond is polar. And so they are all pulling with the same strength, and the tetrahedral shape is a symmetrical shape. And because they are all pulling with the same strength, then they will cancel. The dipoles will cancel because the molecule is symmetrical. It's the same strength for each dipole, and there are 4 of them equidistant from each other. So the polarities cancel and the molecule overall is nonpolar. So this shows like the, electron density around the molecule. And when it's green, it means it's neutral. The molecule overall is nonpolar, which means neutral. The color green is for neutral. Now let's look at CH2Cl2. Here we have a new bond, it's the CH bond. Let's calculate the electronegativity difference for CH. Carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. That's a difference of 0.4. 0.4 is less than 0.5, and that's considered a non-polar bond. So the CH bond is non-polar. We still have the 2 CCl bonds that are polar. And so when we find the Lewis structure and draw the 3D molecule, it looks like this. It's again a tetrahedral shape. We have the 2 hydrogens going to the downward left, and then the chlorines are in the plane here. The chlorines are pulling more strongly on electrons than carbon, so we have 2 dipoles as drawn. And so those 2 dipoles, they will not cancel. They don't cancel because they are not opposite each other, and so they actually add up and reinforce into a net dipole. And so this shows the distribution of the electron cloud. Where it's blue, it's lacking electrons, so it's delta positive or partially positively charged. And where it's red, it's partially negatively charged. It's where you would have the delta minus. So the 2 chlorines are where you have the red area. And so those 2 chlorines are where the net dipole points. It points between the 2 chlorines, starting from the carbon, away towards the 2 chlorines. And so this molecule is polar. Let's practice some more with these 2 molecules. You're given the Lewis structures, and you're given the electronegativity for each of the atoms that are in those molecules. So again, practice this on your own before you watch the answer. So let's start with ONCl. So ONCl, according to the Lewis structure we have here, the central atom is nitrogen. It is surrounded by 3 electron groups because it has 2 atoms bonded to it and 1 lone pair. 3 electron groups, 2 bonded atoms, 1 lone pair. So in the table where you find the molecular geometries, you follow the line that says 3 electron groups, 2 bonded atoms, 1 lone pair, and all the way to the molecular geometry, and it is bent from trigonal planar, right? So we can say trigonal bent. So if we redraw this by taking into account the shape, it looks like this. It's bent. The angle between the bonds is 120 degrees. So the numbers next to each atom are the electronegativity value. So the electronegativity values for chlorine and nitrogen are both 3.0. So there is no polar bonds there. The electronegativity difference between nitrogen and oxygen is 3.5. So the NO bond is polar, and it's polar towards the oxygen, towards the more electronegative element. So we have a dipole going from nitrogen towards oxygen. So is this molecule polar? So we have an asymmetrical shape here, and that dipole, there's nothing that can cancel it. So it does not cancel, and the molecule is polar. And the net dipole for the polarity of the molecule is the same as the dipole for the bond in this case, because there is only one polar bond. Let's look at the other molecule, SO3. You have the Lewis structure. This allows you to determine the shape around the central atom. The central atom here is sulfur. There is 3 electron groups around sulfur. It's 3 bonded atoms, 0 lone pair. So looking at the table where you can determine the molecular geometries, you follow the line that says 3 electron groups, 3 bonding groups, 0 lone pair. The molecular geometry is trigonal planar. So that means it's in the shape of a triangle and it's flat. So drawing this, taking into account the geometry, it looks like that. Triangular shape, flat with all 4 atoms in the plane. The numbers next to each atoms are the electronegativity values for those atoms. So oxygen has an electronegativity value of 3.5 and sulfur 2.5. The difference is 1.0 for each of these bonds. So that means the SO bond is polar. All 3 bonds here are polar, and they're polar the same way. The electronegativity difference is 1.0 for each of them because it's the same 2 atoms. And so the 3 dipoles that are drawn here have the same strengths, the same length. They pull with the same strengths away from the sulfur towards the oxygen. And so we have a symmetrical shape here. It's symmetrical. And so the dipoles, because they are all 3 of the same strengths and pulling in a symmetrical shape where they are equidistant from each other, so they will cancel. They will cancel, and the molecule as a whole is non-polar.